Math 1332, Chapter 10, Probability and Counting Techniques, Section 2, the Fundamental Counting Principle, Permutations, Video 5, Factorials and Permutations. We're finally going to get to what exactly a permutation is, although we've kind of been talking about them a little bit, and maybe you just didn't know it. In the previous two videos, we learned about factorials. To evaluate a factorial for a natural number n, you just multiply every natural number from n down to 1. For example, to evaluate 6 factorial, you just multiply from 6 all the way down to 1, which is 720. It is worth reminding you that there is one version of a factorial that is defined a little bit differently, and that's 0 factorial. We don't run across it too terribly often, but when you do, 0 factorial is defined to equal 1. If you have a calculator with a factorial button, it knows this, so you can just punch in 0 factorial and it will remind you. When the time is right, I'll show you why it has to be 1, but for now we just say it's 1. We also learned that a factorial counts the number of ways to arrange n distinct objects in a row. For example, if a valet had 6 different cars to park in 6 adjacent parking spaces, there are 6 factorial, which equals 720 ways to do that. But what if there were 10 cars to park, but only 6 parking spaces? How many ways can you park 6 of the 10 cars in those spaces? Such a situation in which you park or arrange 6 cars in 10 parking spaces is called a permutation. Here comes the definition, folks. A permutation is an arrangement of objects where the order matters. Notice I didn't say distinct objects because we will look at some situations where the objects aren't necessarily distinct. But in general, a permutation is an arrangement of objects where the order matters. Emphasis on the phrase, order matters. If the order doesn't matter, it's called a combination, but we'll worry about combinations in the next section. So a permutation is an arrangement of objects where the order matters. There exists a formula for counting the number of permutations you can make when you have a certain number of objects, like 10 cars, and you select a portion of them to arrange in some order, like choosing 6 cars to park in parking spaces. But truth be known, we already have a tool for answering this question, the fundamental counting principle. We're going to use it to answer this question, but then try to derive a formula for counting the number of permutations when you have a certain number of objects. We'll start with distinct objects, and you want to choose some of them to put in some particular order. So let's go back to what we did previously and answer the question, how many permutations can you make when choosing 6 distinct cars out of 10? Let's attack it using the fundamental counting principle. And remember, the fundamental counting principle says if you have to make a sequence of decisions and each decision has a certain number of choices you can make, then the total number of ways you can collectively make your decisions is by multiplying the number of choices you have for each decision. When you're using the fundamental counting principle, it sometimes helps to draw some blanks like this. 1 blank for each decision you have to make. We have to decide the first car to park, then the second, and then the third, the fourth, the fifth, and the sixth. And then for each decision, you write down the number of choices you have for that decision. For the first car, there are 10 cars to choose from, so our first blank has a 10. But after we park that car, how many choices do we have for the second car? Not 10, because we can't park the first car again, but 9. And then after we park that car, there are only 8 cars left to choose for the third parking space, and then 7, and then 6, and then 5. If we multiply all these, we get some number. I'm not going to waste time trying to do it in my head. I'll just open the calculator on my computer and punch in a few things. And we get 151,200. So we kind of already have a way to do this. But notice that the problem that answered the question, 10 times 9 times 8 times 7 times 6 times 5, is sort of like a factorial, but not quite. It's kind of like a factorial because you started a number, in this case 10, and you start multiplying each number less than that. But if it were a factorial, it would go all the way down to times 1, and this one doesn't. So we can't just say that to calculate the number of permutations of selecting 6 out of 10 cars, we can't just say it's 10 factorial because it's not. However, if you view this problem, this multiplication problem, as the result of simplifying a ratio of factorials, something emerges. I'm going to do something that's not very common in math. I'm going to unreduce a fraction. Reducing is easy. You look for factors that match on the top, on the bottom, and you cancel them. But how do you unreduce? How do you know what was canceled? And the answer is you don't. But I'm going to unreduce this with the intention of restoring the 10 factorial. Because right now the answer, or the problem that answers this question, is not a factorial. But what if it used to be a fraction that was a factorial on the top? So it would have to go all the way down to 1. But that got canceled with stuff on the bottom. So if we had something like this, then the top is a factorial. It's 10 factorial. And the bottom is also a factorial. It's 4 factorial. And like in the previous video, if we expanded both of those, we could cancel the stuff in blue and we would be left with the stuff in red, which gave the answer to the question, how many ways can we park 6 of the 10 cars in those parking spaces? So a problem like 10 times 9 times 8 times 7 times 6 times 5 is not a factorial by itself, but it can be viewed as a ratio of factorials. From this, we can see that the number of permutations you can make by choosing 6 out of 10 distinct cars is equal to 10 factorial over 4 factorial. Because if you roll it out, you would cancel everything from 4 downward and be left with 10, 9, 8, 7, 6, 5. I forgot what this says. Well, oh, but where did the 4 come from? The problem started with a 6 and a 10. If you pick 6 out of 10 distinct cars, I think it's pretty obvious that the 10 was given to us in the problem, but where did this 4 come from? Well, you have a 10 and a 6, and you get a 4. Did the 4 come from 10 minus 6? The short answer is yes. Yes, it did. Oops, we're almost ready for there. So let's see if we can take the problem that gave the answer to the question, which was 10 factorial over 4 factorial. In fact, let's go all the way back to where we started, 10 times 9 times 8 times 7 times 6 times 5. And let's see if we can write this so that it involves nothing but the numbers that we were given, the 10 and the 6. Well, we've already seen that we can rewrite this as 10 factorial over 4 factorial. But we weren't given both of those numbers in the problem. We were given a 10 and a 6. But if we rewrite the 4 as 10 minus 6 in parentheses with the factorial at the end, look at this expression and look at the original problem. The expression highlighted at the bottom involves only the numbers that we were given. 6 out of 10 distinct cars. This problem down here calculates the number of ways we can pick 6 out of 10 cars in a certain order, and that expression only involves the numbers we were given. What we're doing is building a formula, and the formula goes something like this. Oh, I'm sorry, before we do that, one last thing. There is, first off, I misspelled permutations. Let's fix it. There we go. There is a notation for the number of permutations you can make by choosing 6 out of 10 distinct cars, or 6 out of 10 distinct anything. The notation for the number of permutations you can make by choosing 6 out of 10 distinct cars is capital P for permutation, and it has two subscripted numbers, one on the left, one on the right. The one on the left is the total number that you're selecting from 10 cars. How many permutations can I make by selecting 6 of them? That would just be read 10p6, but it means how many permutations if I pick out of 10 cars, I pick 6. Let me say that again. If I have 10 cars to pick from, how many permutations can I make if I pick 6 of them? Formula time. The number of permutations you can make by selecting R out of n distinct objects. I did not choose these letters, these variables. They are pretty standard for this type of problem. But the number of permutations you can make by selecting R out of n. Remember, the number on the left is how many you're selecting from, and the number on the right is how many you're actually selecting. The number of permutations you can make by selecting R out of n distinct objects is NPR equals, had to pause for a sneeze, NPR equals, well, let's look at the previous example. The number on top has a factorial, and the number matches the total that we're selecting from, which means the top of this formula is going to be this number with a factorial. The number on the bottom came from subtracting the two numbers and then sticking a factorial on it. So if we subtract the two numbers and then stick a factorial on it, we now have our formula for how many permutations can you make out of n objects if you select R of them. I know what some of you might be thinking if you're still watching this video, why didn't you start with this? Because I told you from day one that I'm trying to make you better thinkers and better problem solvers, and just saying here's the formula doesn't accomplish that. But we are going to use this formula, so know it, put it in your notes, expect it on your test. Let's do an example real quick and wrap up this video. This one will sound familiar. 10 people enter a race. The winner gets a gold medal, the second place finisher gets a silver medal, and the third place finisher gets a bronze medal. How many different ways can the medals be awarded? Notice nowhere in this problem does it say how many permutations. But part of the process that you're going to have to go through in doing some of these problems is asking yourself, is this asking for the number of permutations, or is this asking for the number of combinations? I know I casually mentioned combinations as a side note a minute ago, but the key thing is that permutations, the order matters. So before you use the permutation formula, you have to ask yourself, does the order matter in this situation? In this case, does the order matter in which they finished the race? The answer is yes. If you finished first, it's different than finishing third, which is different than finishing 10th. First gets a gold, third gets a bronze, 10th gets the satisfaction of being beat by everybody else in the race. Guess that's not really satisfying. But yeah, before you grab the permutation formula, you have to ask yourself, does order matter? So since the order of finishing matters, this is a permutation problem. And once you've decided it's a permutation problem, then it's fairly straightforward. Because now all you have to do is ask yourself, how many people are we selecting from and how many people are we selecting? Well, there are 10 people running the race, so we are selecting from 10 people. This is a permutation problem. We are selecting 3 of them to finish the race. Well, we're not selecting, we're counting the number of permutations. Who gets first, second, third depends upon how fast they run. But if we're counting the number of permutations, it's like we're saying, well, how many choices could there be for the first place and then second place and then third place? So 10P3 out of 10 runners, how many permutations are there if we pick 3 of them? According to the formula, it's a ratio of factorials. The top is the first number, but the bottom is the difference of the two. Or rather, I should say, the top is the factorial of the first number, but the bottom is the factorial of the difference of the two. There's your setup. I'm not gonna expand the 10 factorial yet. I do want to go ahead and call 10 minus 3 7. But I want you to think about this before I write it out. If I wrote out both of the factorials, 10 all the way down to 1, 7 all the way down to 1, ask yourself what would cancel and what would be left over. If we started writing the 10 factorial, it would go 10 times 9 times 8. But then it would go 7 down to 1, which would cancel everything from the bottom. This is only going to be left with 10 times 9 times 8. Because everything from 7 down will cancel. And that's 720. So if you're asked how many permutations, or if you're just flat out given a problem like this, and some of the homework questions start there, then it's the first number factorial over the difference factorial. A lot of canceling happens, and then whatever's left is left.